All right, maybe that's long enough. Welcome, everybody. Thank you so much for coming along to this first showcase event. My name is Nick Hamilton. I'm a senior machine learning consultant at the Research Computing Centre at the University of Queensland, and also Institute Biomathematician at the Institute for Molecular Bioscience. And I'll be chairing the first half of this series of talks. So this is being presented by the Machine Learning Community of Practice, which is part of an ARDC-funded collaboration between Monash and UQ to develop and support machine learning communities, both locally and nationally. And this particular event, which is part of three, is being presented in collaboration with NCI and Palsy. And the aim of this is to be able to identify sort of common opportunities, gaps and challenges in applying machine learning, and to sort of share experiences and bring the community together. We've got a fantastic range of 6 talks together from 2 continents. The theme is largely around imaging, though we have got one that's slightly left of field on that. We've got people coming in from Monash, UQ, RMIT, Deakin, and even the Max Planck Institutes in Germany. So we hopefully will bring a very wide range of experiences to bear. So the structure of this is we're going to have 2 blocks of talks, 3 talks and then some time for questions, and another 3 talks and time for questions. So each speaker will have about 15 minutes, and we hope to have time to ask questions of the speakers once they've spoken. So if you want to pop questions as you think of them into the chat, then we can ask them if we have some time at the end of their talk. But then at the end of each block of talks, we'll have about 10 minutes or 15 minutes where you can ask general questions. So if you've got questions about roadblocks in developing machine learning, or particular problems you've encountered, or comments you'd like to make, would welcome you to make contributions there. So I'm going to be very brief with my introductions for the speakers, because I just want to get on with speaking and talking about what they've got. And no doubt you've had a chance to read the document which gave the sort of abstracts and bios anyway. So first up, we've got Mitchell Hargraves and Richard Bassett from Monash, and they're going to be talking to us on forensic facial reconstruction. So if you're ready, Mitchell, I'll hand over to you, and if you'd like to share your screen.
All right.
Thank you so much. So I remind you, pop questions into the chat if you've got any.
Okay. I'm assuming everything's fine. We good? All right, cool. Yeah, so this is a project that I was working on with Monash Deep Neuron. And Richard was helping us on the forensic side with this. So this is the rather long list of project members that we've had and supervisors. Big thanks to Chris Bain for first helping us to get this project, and for Richard and Xiaojun for supervising us. Richard will be also talking with us today to give us some of the background of the problem. First thing that you might notice is that there are a long list of project members. That's largely because the project was done by undergraduates. And so we had a rotating cast of team members depending on like when they graduated and so on, which played all sorts of havoc with the ethics process, but we'll talk about that later. Richard, if you would you like to take the slide?
Certainly, Mitchell. Thank you. Thanks, everyone. And thanks, Mitch, for asking me to come along. So I'm head of the Department of Forensic Medicine at Monash Uni and Deputy Director of the Victorian Institute of Forensic Medicine. And in my day job, we deal with all deceased people who are admitted to the Victorian State Coroner. One of the primary tasks of the State Coroner is to identify people in a robust manner as possible. And there's all sorts of methods. We've got DNA, we've got dental record comparison, we've got fingerprints. We have a whole list of methods, but occasionally we come across a set of human remains, skeletal remains, that are unable to be identified by any other method rather than other than trying to reconstruct a face on those human remains. Traditionally, that's been done by putting clay on skulls and building a face. You all would be familiar with the forensic artist concept of, you would have seen it done on Egyptian mummies. You would have occasionally seen it in newspapers as a reconstruction of how someone might have looked in life. But those are all artistic impressions and they're not empirical, evidence-based methods of reconstruction. So at the Institute, we have something like 90,000 full body CT scans in our database of every deceased person that's been through our institute. And we can use that data the plan is to use that data to attempt to train a machine learning algorithm such that you can reconstruct a face on a skull. That's what the Deep Neuron team has been working on for the last couple of years. So Mitch, you can take off from there.
All right. So as Richard was just saying, the goal was to apply generative techniques. So generative adversarial, we ended up using again, directly to the problem to create an end-to-end solution, meaning that we can bypass the subjectivity of a forensics artist and just have a repeatable process where you can input a 3D model of a skull and output, hopefully, something that is recognizable. At the end of the day, we ended up with 1,300-ish CT scans, which we then split by train, validation, and test. There was a good portion of these which we had to remove from the data set due to head trauma, which will obviously impact the structure of the skull. Large medical instruments, some of them had like tubes coming out of their mouths and other things, which we probably didn't want in our labels. And some of them also were just very awkwardly positioned, like the face inside of the pillar, for example, other shenanigans like that. So at the end of the day, we ended up with 971, which we could use for training and validation and testing. For pre-processing, we ended up converting these scans into NumPy. And we used thresholding based on density to create the labels and the inputs. We also ended up hard coding in rotational augmentations to help address the relatively small data set size. So as you can see from the flowchart on the right, we also, as you can see by like a pull up, can I? No, I can't. Okay, never mind. I was going to do laser pointer. That's okay. There was quite a lot of noise present in these scans. So we ended up using Gaussian blurs to try and remove that. And we also had to be quite aggressive in how we cropped it around the face and removing the neck because the shoulder structure isn't what we're interested in. It also helped us to reclaim some of those scans back from having random medical equipment positioned around the head. After all that process is done, it then splits off into skull and face, which we then convert to a depth map. More on that later, but rather than addressing the problem directly using 3D convolutions, we discovered that we were able to get much better results using a depth map. So that is the distance towards the first non-air pixel of the skull or the face, depending on which it is. So this is what a model looks like after it's been converted. As you can see in the first one, there are lots of things in the background. That thing that you can see behind the head is, I believe, a pillar. We then crop around the head using a bunch of algorithms that we developed to then detect where the chin is and the sides of the face, which gives us a relatively clean head, which we then convert, as I just mentioned, to a depth map. This is the model we ended up going with. As I mentioned before, it was an adversarial approach. So we have a generator and a discriminator. But rather than training them in tandem, the generator really is the star of the show. We pre-trained it first and then used no-GAN training to, I guess, augment it with adversarial loss just in the last section of the training. Section by section, this is the generator downsample path, which you'll notice is literally just a ResNet, which meant that we could then take advantage of existing training off of ImageNet. Of course, ImageNet is very different from a depth map, but we discovered that it was close enough that if we duplicated, or I guess triplicated, the input so that we had RGB, we could then pass it in and it would still work well enough. ResNet training, sorry, ImageNet pre-training seemed to work significantly better than not using any training whatsoever. Perhaps in a future version of this, which was actually able to use the full data from VIFM, this won't be necessary, but at least with the amount of data that we had, it was required. We then upsample using pixel shuffle and self-attention. One thing that we did was, again, taking advantage of the 2D modality, we were able to use perceptual loss from the VGG phase 2 dataset. So there was a ResNet 34 that was pre-trained on VGG phase 2, and then the outputs of those feature maps we then use as our loss rather than directly comparing the pixels. The other thing you'll notice is that we have these crosses coming over the edge, and that is for our discrimination. If you haven't seen this before, it might look a little bit funky. This is multi-scale gradients. So rather than only looking at the final generation, we compare each of the outputs of the feature maps. And you can replicate this with a label, even though it hasn't gone through the full model, just by downsampling the image, which hopefully means that you are training your generator and your discriminator to now look at not only the full image, but also the intermediary processes, so that you can encourage it to, I guess, upsample effectively. The other thing which you might notice is this concat pooling block, which is a little bit non-standard, but we found that worked better. As I mentioned before, this is with no-GAN training. So essentially there's a threshold. We train a generator for one cycle, that is one batch. And then we continue to train the discriminator until the discriminator drops below a given threshold and loss. And we found that doing that works better than, at least in this circumstance, so that we can take advantage of pre-training, than training them according to any other schedule where we just alternate between them. This is just to make sure that the discriminator is always feeding useful loss to the generator, and we're never going to end up with a situation where, I guess, the generator gets thrown off and we waste all our pre-training work. The biggest challenges that we faced included the size of the 3D files. It meant that it was rather difficult to visualize what was going on, and it meant that we needed large amounts of memory. When we first started the project, because we didn't really understand how to use HPC properly, there was a lot of floundering around on laptops, which was somewhat difficult because we always ended up running out of RAM. We had to downsample the images quite significantly in order to actually view them in 3D. And I understand there are DICOM viewers which theoretically wouldn't require this, but that doesn't help you when it's a generation. And what you effectively have is a giant NumPy file. The second thing that we faced was the lack of available data within depth maps. But we found that using RGB was fine enough. It's close enough, even though you'd think it wouldn't work. And so we were still able to make use of those weights and for the perceptual loss function. We found that using the model in 3D with 3D convolutions wasn't as effective, just because of the number of parameters required and the little data that we had. And so converting towards depth maps meant that we could then use standard 2D convolutions. We also found there were lots of issues with getting access to the data. There was a huge period of time at the beginning of the project where we didn't have any data at all, just because the original plan for transferring didn't work very well. At the end of the day, we ended up having to go in with a hard drive and encrypt that. And that was only 350 of the original amount that we'd requested, which was 5,000. at the end of the day, we still didn't end up getting that 5,000. And this is largely because of the way that the database is structured. I'm not sure the current status of that. I don't know if that has been resolved. Richard can probably let me know what the actual details are at this stage. But during the process of the project, that was one of the biggest issues. As I alluded to earlier as well, the ethics agreement also did not play well with the fact that we were undergraduates with rotating members. It meant that every time a semester changed and someone graduated and we needed a new person, that we would have to put in another ethics request, which would in turn sometimes take several months to get back. And so there were all sorts of problems with that. I suspect that won't be as much of a problem with more traditional internships, but the model that we had did not play well with this. I suspect that might be idiosyncratic to us though. These are the results that we got in 3D with 3D convolutions. In order to get it to fit VRAM-wise, we had to downsample it quite significantly. And as you can see, the outputs are not particularly good. You can also see the graininess of the labels, which definitely contributed to the problem. But this is what we were able to get in 2D. You have the input on the left and the label all the way on the right. The best model that we were able to achieve is second to the right. As you can see, it's significantly better than 3D. And what you're essentially looking at is an ablation study where each new column adds an extra technique, with the second and third column being baselines for purely generative approaches. We're quite happy with these results. We know that they could be improved with more data. We know that we could be improved with more development as well. We were very much rushing for time at the end. But under the circumstances, I think this does demonstrate that deep learning can be directly applied to this problem and that there is promise in this field. Okay, and passing over to Richard to wrap us up.
Thanks, Mitchell. Regarding your issues with the data, it was difficult because we're a service organisation and not directed towards research. So the data is subject to all sorts of coronial issues, medico-legal issues with privacy, confidentiality, de-identification, et cetera, so it makes it difficult to get. That's
not so much a criticism.
No, I know. We have now recently managed to get a dedicated research server. So we've had the last 5 years of post-mortem CT scans transferred onto this research server, which is going to make data access far more simpler and far less bureaucratic. So that's moving forward. But I'm really proud of the team and the way these guys have worked this problem and the fact that it does show really good potential for further development. And so the next stage in this research is to further develop the machine learning models on a larger data set, also incorporating some advanced DNA techniques we use, whereby we can take a sample of bone from somebody, extract the DNA, determine hair color, eye color, skin tone, ancestral background, etc. If we incorporate that into the machine learning model, it'll give us a much more realistic picture of a person. And then we're going to get a forensic artist to reconstruct their particular facial reconstructions on these unknown skulls. We'll use a subset of data for that, probably 30 or 40 cases. So we'll have forensic artist reconstructions, we'll have machine learning reconstructions with the DNA technology, and we'll have the original photographs of the actual person. So then we can go through a comparison process via two ways. One is a panel of people looking to see which one looks the most realistic, and the other way is trying a variety of facial recognition software packages and seeing how the matching goes in that respect. So that's sort of the next stage of the process from now on. But Mitchell and his team have done a fantastic job with the help of Xiao Jun and Chris Bain, and it's all power to them. I'm completely illiterate when it comes to machine learning, being a forensic medicine person. So I've just been sort of gobsmacked by the knowledge and skills that these guys have.
Great. Well, thank you very much, both of you, for a fantastic talk. We're out of time really, but we've got a couple of questions. The first was from Adam. He said, could you train it to handle fractured damage samples by removing parts of the skull volume artificially and train your GAN further?
Theoretically, I don't have to run the experiment.
So that's another project we've got going. Is we have quite a lot of people who are traumatically injured, and that actually impacts on the pathological analysis and medico-legal investigation as well. So we're looking at ways of reconstructing disrupted anatomy, not only in the skull but in the rest of the body as well, to make it more normal, and that'll give us a much better indication of what has actually happened to this person. So that's another project that's sort of probably a bit further down the pipeline.
Great, thank you. And one other question from Suhag. What evaluation metric did you use for it, and any particular techniques you use for preventing model collapse when training the GAN?
So we were using IOU and chamfer loss for strict evaluation. As I mentioned before, we were using perceptual loss for training in addition to the FS-Arial. So because we were pairing the two losses together, we could rely on the labels to avoid mode collapse. That being said, though, if I go back a few, you can notice that all these noses look suspiciously similar. So some amount of mode collapsing did happen. Right. That being said, though, I mean, the nose doesn't exactly exist on the skull. So I think we can cut the model a little bit of slack, given that we didn't have that many examples of noses for it to run off.
Okay, well, thank you very much for that. In the interest of time, we better move on, but it was fantastic and very informative and exciting project. So next up, we have a talk from University of Queensland, Dr. Stefan Bollmann, and he's going to be talking about enhancing the speed and robustness of magnetic resonance imaging applications using deep learning. So over to you, Stefan.
Cool, thank you very much for the introduction. I hope you see my screen.
Yeah, you're good.
Okay, perfect. Cool. Let's get started. So what I would like to cover today is 3 examples from our work. And I hope that some of these things that we discovered and learned, that this is also helpful to others, and then we can maybe discuss a little bit later. So the first example I want to show is we build a model purely based on simulated data, because we're trying to solve physics problems. And for this, we can actually simulate our data completely. And also make sure that the model is actually consistent with the physics. Another example I want to show is where we don't really have a physics model, but we can check our outputs and make sure they're actually plausible. And the third one is, how do we share our models with readers, for example, of a manuscript? So we did a couple of things there, and I want to show that. So let's get started with the first project. So just quickly motivating, what is actually our problem that we're trying to solve? So in magnetic resonance imaging, we would like to distinguish between lesions in the brain. Lesions can be either fresh, so they can be actively bleeding, or when they are old, what the brain does is, or the body does, is they put calcium around it, so they're calcified. The problem is, it would be really good to understand which lesions in the brain are old and which ones are new, but in MRI, we just see this dark spot in both cases. So no matter whether it's a calcification or a bleeding. However, there is a technique that's fairly new that's called quantitative susceptibility mapping, which can differentiate between these two. So a bleeding would be in white and a calcification would be in black, which would be really cool. Problem is, this is computationally quite expensive. And why is that? Well, when we think about the physics, we have a magnetic susceptibility distribution or a source. And when we put this in the magnetic field, what we get is we get a field perturbation of the magnetic field. And this field perturbation will be different if it's blood or a calcification. So now the good thing is we can describe the forward model fairly simplistic. So it's just this integral, and we can compute this. So this is easy. The problem is, when we go from the field perturbation back to this magnetic susceptibility distribution, this is hard. This is an ill-posed inverse problem, because when you think about it, there could be infinite different source configuration that could lead to the same field. So what we currently do is we run very expensive optimization algorithms that run for thousands of iterations until they find a solution that's good. And the problem is this takes too long. So in a clinical application, this would take hours, and we only have minutes to get these images. So this is where we thought, well, let's use deep learning to speed up that process. And what we did there is, as I said, we don't really have a lot of examples, or we didn't want to use examples of the traditional techniques. We actually know the problem. So what we did is we simulated distributions of sources. We have this forward model that we can describe, and then we just computed lots of examples of these well-posed forward problems. And in this case, we simulated about 90,000 examples. And then we trained a normal UNet to learn the inverse of that. And then when we got this model, we first tested it on data that was very similar to the training data. So we just, again, simulated a couple of these shape configurations. We applied the forward model, and then we ran it through our model, and we were quite happy to see that it actually works. And also in comparing to traditional technique, it looks very similar, and we can almost recover the ground truth. Now you would say, well, this is simple because this is what you trained with. What happens if you use real data? And to our surprise, this also worked. So on the left, you see the input, and on the right, you see the reconstructed brain scans. And the good thing is that since our physics model is quite simple, we can learn to invert that problem. And because we trained on these shapes, it now also works in the brain or in the rest of the body, which is quite nice. And also because we don't need 1,000 iterations, we only need 1 minute compute time. So this now is also fast enough to run it on the scanner. So then we thought, wow, we did it. Let's run this on the MRI scanner. The problem is, what we quickly realized, this model is not that stable because we're using a UNet, and I'm pretty sure other people have seen this as well. When you take a very well-trained UNet, which is perfectly trained on the training data, and you add a little bit of noise to it, or you add an offset to it, this whole thing breaks down very, very quickly and miserably. So you see that in the right side, we just added a little bit of noise. The traditional technique is fine because it's an optimization. It's built for that. The deep learning completely falls apart. So it doesn't even work. It completely goes outside of its range. So we thought, okay, what can we do? So this is now work of a master student in our group, Francesco, and he started and built traditional optimization into our deep learning algorithm. And this technique is called a variational network. So you can basically use that if you can describe your data model and you can have a data consistency term, you can actually put that into your optimization and into our network. So what we did is we take a standard optimization, and instead of running it for thousands of iterations, we only run it for 6 iterations. So it's still a lot faster than the traditional optimization, but we use a neural network as a regularizer. So instead of in the classical case, you would use something like an L2 norm or an L1 norm. So you either enforce sparsity or smoothness. And with the neural network, we can learn much more complex priors that are much better suited for the problem. And when we use this for our data, we see that it actually, our idea works. So now the traditional optimization, as I said, takes very long, but it's not annoyed by noise. Our agnostic deep learning approach in the middle falls apart immediately. The variational network works and also is even more robust to noise than the traditional optimization, which is quite nice. And yeah, we're currently working on writing that up. So the second example that I wanted to show is slightly different because here we can't describe our model because we don't know. And this work is driven by a PhD student in our group, Sharok, who just finished. And I quickly show what the motivation is behind it. So in MRI, you can think about an MRI, it's like a big mobile phone. So we emit radio waves, and these radio waves heat up tissue. So we can describe that with the specific absorption rate, SAR, same thing as a microwave or a phone. And we are limited in how much SAR we can apply to a human body because we can't heat up the tissue because that's not healthy. And because of this, our scans take artificially longer than they need to be because we have to basically apply these pulses and we need to wait until the tissue cools down again before we can apply the next pulse. And this really, extends the scan time unnecessarily. Now, if we would know this field distribution inside the brain, for example, so this is what I show in the right here, we call that a B1 map. If we would know that, we could tailor our pulses. So we could, for example, say, well, in the middle of the brain, I need a lot more energy, or no, actually, I need a lot less energy in the middle of the brain. And on the edges of the brain, I need a lot more energy. So I could tailor the pulse and I could save SAR. And with this, I could save time. The problem is that to get this information, I need to run a scan that takes 2 minutes. And in the end, I will only save 1.5 minutes. So it's absolutely not worth it. I spent 30 seconds more. And we thought, well, can we somehow extract this information from a scan that we acquire anyway? And the reason that we thought this is possible is this field distribution is an artifact as well. So this is very much hidden inside this localizer scan as an artifact. So we thought, can we train a network that recognizes this artifact and extracts that information from it? So again, we used our beloved UNet and put in these localizer scans and our B1 maps that we scanned. And then we tested it. So we, in the middle, you see what we wanted to learn. So this is the physics ground truth that we measured. And on the right, we see what the network predicted. And the good thing is, it's quite close. It's not perfect because it can't be perfect because we're extracting this from, as I said, an artifact basically, but it's close enough. And what we then did is, because we were not perfect, we need to check our results. And this is what we did. So we take our results we get from the network and we feed them through a physics simulation. So we check if the results are actually plausible and they do what we want. And I show this here. In blue, this is where, with our predicted results, we are okay with the pulse. So everything works. Green is at the edge of working. So this is where things could go wrong. And then red is where it goes wrong. And with this, we can then see if we have red stuff in there where we just need to increase the pulse power a little bit more until we don't have anything red. But the cool thing is in the rest of the brain where we can be sure that we are okay and we're actually doing the right thing. And then the final results are that we actually save about 1.5 minutes scan time. So in the first column, you see the standard, what we currently do. So the sequence runs for 3 minutes, 20 seconds. And then we have 1.5 minute delay time where we need to wait for the scanner and for the tissue to cool down. In the middle, you see what we could have done. We could have spent 2 additional minutes to calibrate our pulses, but then again, we end up with 30 seconds more. Or on the right side, you see with a neural network, we save these 2 minutes and we don't get a delay because we calibrated our pulses nicely. And yeah, we're much faster and it's robust because we check the results. Okay, and the final thing I wanted to show is how to share or how we shared our models with the readers. And the reason I wanted to show this is we had a lot of, we had very curious reviewers, I would say. So our reviewers said, well, we don't believe you. This is all, this sounds like magic. You're extracting something. This can't be true. So they wanted to see all the source code, and just dumping the source code to the reviewers didn't help either because they said, well, I can't run it. I don't have a GPU. I don't know how to install TensorFlow. I don't even know what TensorFlow is. So that was quite interesting. So we said, okay, we have to do something to make that accessible to our reviewers and also to the readers of the paper, because we wanted that people can try that and can extend on that idea, because it's quite cool, because we can save potentially a lot of time in MRI and solve a lot of other problems that are very similar to this. So what we did is, instead of just zipping up all our code and data into a giant zip archive and putting it on Dropbox, we did something else. And the reason why we think this wasn't so cool is, if someone just wants to see a single function and has to download 2 GB of a file, well, that's not cool. And then we thought, well, what happens if people don't have MATLAB or don't have Python or don't have TensorFlow? Then we also need to do something about this. And also, what if Dropbox stops to exist? And this link then is in the paper and people can't access this data in 2 years' time, which happened in the past. And then also, what if there is a bug in our code, which is highly likely because we have 1,000 lines of code. So there is probably 10 bugs in there and that we haven't found yet. So how do we update this later, right? So we said, okay, let's think about this a little bit. So we built a couple of things there. So first we used a cloud-based platform to host the data. And for this, we decided to go for the Open Science Foundation, which I can highly recommend. It's a service founded by Brian Nosek for reproducible neuroscience. And they have a preservation fund. So they will be around for the next 50 years at least. They provide digital object identifiers, which we can then use in a paper. And the cool thing is there's also an OSF client where we can upload our models and data directly from the high-performance computing clusters where we trained our models directly to the Open Science Foundation. So we don't have to even go on a website and manually upload things. So we can just script everything, which was very nice. Then instead of assuming that people have a GPU and they can install TensorFlow correctly, we just build a Google Colab notebook. And we just set everything up for them so they can just click play and they can see everything. And if they're happy to run it on their own computer, they can just take the code and run it. And also you see something in here. We haven't mentioned the Google Colab link in there. We don't even mention that this runs on Google Colab. And we did this on purpose because Google is known for just killing their products every few years. So we thought, well, in 2 years, Google Colab is probably not around anymore. So we made it very flexible. So this can run on pretty much any cloud provider that has GPUs at a Jupyter instance. So we made it quite general and not specific to Google Colab. We just use Google Colab because it was the only service right now that offers GPUs for free for everyone. Another thing we did is for for the people who just want to use our models directly, we put it all on GitHub. So people can just check out our code repository. And also we provided the Git hash that we used in the paper. So this also gives us the possibility of updating the code later. And people can still go back to this commit hash and reproduce the results in the paper, including potential bugs that we probably have still in there. And then also, the Open Science Foundation gives us this whole possibility of updating everything. So we can update the data, we can update the link to the Google Colab notebook or to the next version of Colab that could come in a few years. And this link will basically always stay and keep everything up to date. That's in the paper. Yeah, so that's what we came up with. So hopefully that is useful to someone, or maybe we can also discuss what other people do in this space. And our society journal, where we published our paper, they liked that quite a lot. So they actually interviewed us and said, well, can we do a blog post about this? Because that's quite useful to know. And we got featured in our society journal for that. Yeah, so for this, I thank you for your attention. And if you want to know more details about this OSF client is uploading, I have a couple of tutorials on the website, mri.sbollmann.net. So you can just check that out, or just send me an email and I'm very happy to help.
Great. Well, thank you so much for that, Stefan. That's beautiful work. We're a bit short on time, but we've got one quick question. Mateus asks, if you link your GitHub repo to Zenodo and tag that commit as a release, Zenodo will archive your source code and give you a DOI that you can use for citation. Also, it's comments rather than a...
Yes, I know. That's correct. And yeah, that works very well. So Zenodo works quite well for that case. Yes. Yeah. And we achieve the same thing via OSF. So OSF does exactly the same thing. It makes a snapshot, provides a DOI. So Zenodo is just a different service.
Yeah, I think this is just awesome, the way you're putting all of these things together, because there's so much research code, as everybody knows, just dies and is unrunnable. And yeah, it's fantastic. So one quick question on the first two projects. So are those now sort of out in the wild now and being used by other researchers?
Yes. So the first two projects are out in the wild. Yes, people are using it. And yeah, so we're also currently working on implementing these on the MRI scanners with Siemens, the vendor of these systems, to bring that into the clinic as well, which then showed a lot of more problems because deep learning is, I think, still too fragile to use in production in medical fields, because that's the thing. Siemens has to know that this has to guarantee this will work, right? It has to go through FDA and everything. So this makes things quite difficult, actually.
Okay, well, thank you so much, Stefan. In the interest of time, we better move on. So next up, we have Sheriff Tawfiq Abbas from Deakin, and he's going to be talking to us on machine learning for material discovery. So Sharif, are you here? Does anybody know if Sharif is here? Oh, this is interesting. Okay. Well, in that case, perhaps I'll open things up to a more general discussion. So we plan to have sort of 10 or 15 minutes for general sort of questions around machine learning that you might have. So maybe there are roadblocks in what you're currently developing yourself. Maybe you've got a question you'd like to ask the community about how things, how they've solved a problem, or something that you've worked on that you haven't been able to solve yourself yet, or maybe around future needs. So does anybody, so feel free to sort of turn on your microphone and or camera if you'd like to make a comment or ask a question. And please do ask one. Otherwise, I'm just going to have to fill in and tell jokes or something.
Hey, Stefan. I have a question regarding the OSF that you mentioned. So do we have something equivalent in Australian universities where researchers or the institutions have got together and made anything similar to OSF?
Yes and no. Okay, so I didn't go into more detail there, but I will actually give a talk for AARNet on the 5th of August, where I show the OSF integration with AARNet Cloud Store. So what you can do, you can just upload your data on Cloud Store, and you can link your Cloud Store account to the OSF. So the OSF is just a wrapper for different storage techniques and GitHub and different things. And then you can actually have your data there as well. And also, if you don't want to use OSF because it's in the US, or you want to use purely something Australian, the Cloud Store provides something they call a dataset collection, a snapshot, where you can also take a subset of your Cloud Store thing, archive it, provide a DOI, and make it eternal, basically. If that answers your question. And also there is, for example, if you don't have deep learning workloads, for example, the Swan notebook of Cloud Store works quite well as well for reproducibility. The problem is it's not accessible for people outside of AARNet or outside of Australia. So that's why I didn't use it, and it didn't have GPUs.
I see. Can you just link anything that I can use? The SwanNet and the other one that you mentioned?
Yes. I will post some links in the chat. Yes, and then someone posted this link. Yes, exactly. So that talk, I will show a little bit how to link this up, and I can post the dataset collections and the Swan. Yes.
Thank you, Stefan.
I've got a question for Project One. Your last slide, I think you mentioned an interesting being able to source more data. I was interested in what data that might be, but also more generally about the data sets that you used. You used ImageNet, RGB, VGG Phase 2, and any comments you might like to make on those data sets as sources for your work.
Apologies, I've shut down from my regular computer, so friend will have to do. I was largely referring to more images of skulls and faces. So more data from Victorian Institute of Forensic Medicine. They have a lot more data than they were able to give us due to the structure of their data. So more examples of the actual domain that we're interested in would be much more beneficial. Something that you could do rather than pre-training on ImageNet would be something like Celeb A, which is obviously much closer because that is a lot of faces. We didn't experiment with that kind of thing just due to time.
I guess part of why I'm leading that question is to do with, well, I'm assuming, for example, that a lot of the people being looked at forensically have very diverse ethnic backgrounds, and that a number of the data sources that you've used potentially represent very different cohorts. And so I was just wondering if that was also a driver to actually look at other ways to get more representative data into your model.
You are absolutely right. Ethnic representation would be very important in anything that was actually put into production. It was something that we were very aware of. We were basically just making a proof of concept.
Yeah, yep.
With the amount of data that we had, nothing, like even if it did produce fantastic results, it would only ever be able to produce like something that was representative of what was in the training set.
Yeah.
As you've identified.
Yep.
So yes, you're right. It is a big problem.
But if you were to take your idea kind of into production, that would be one of the big challenges for that, wouldn't it? Yeah.
Yes, you'd have to make sure that the data that you had was well balanced and diverse.
Yeah, cool. Thank you.
You're welcome.
So just a quick update, Nick. I've tried reaching the third speaker.
Yes.
And not heard back yet, but if you want to progress with the next set of presentation after the discussion, if he appears, then we can do it at the last.
Yes, I think we'll do that. We'll continue with the program, and maybe if we've got any further questions at this point, has anybody got any other comments or questions? If not, yeah, perhaps we'll see if Sheriff shows up again later, and if it does, then we'll. Oh, hang on, Nimol, have you got a question? You put your hand up. Oh, perhaps not. Okay. Yeah, so we'll come back to Sheriff later if he shows up. But for now, I might hand over to Adam Morris, who's from Monash, and he's going to chair the second part of the session. Thanks, Adam.
Thanks, Nick. That's right. I'm a research fellow at the Data Science and AI platform at Monash, and I'm also involved in the ARDC machine learning project that's behind the ML4AU community of practice that we're involved in right now. Our next presenter is Titus Tang, who is also from the Data Science and AI platform at Monash. He's a deep learning engineer in our group, and he's going to present work as part of a collaboration with Dr. Michelle Anandaraja on detection of lung infections. Thanks, Titus.
Thanks, Adam. I'm not sure if you can see my screen because the usual green box that appears around my presentation is not appearing.
All good.
Oh, good. Thanks. All right. So I'm here to talk about fungal AI, which, as Adam mentioned, is led by Dr. Michelle Anandaraja from the Alfred Hospital and is supported by the Monash Data Science and AI platform. So just very quick notes about me. I'm a deep learning engineer on the Data Science and AI platform, and I'm one of the engineers working on this project. I'm not a medical professional, so some of the medical stuff that we are very briefly touching on in this presentation is a little bit out of my depth. And also to note that I'm presenting on behalf of a team of radiologists, infectious disease experts at the Alfred, and also various deep learning and software engineers. So this is not fully my work, it's the work of an entire team. So let's talk about fungi. Fungi is its own unique kingdom. It is not a plant, it is not an animal, it is its own unique kingdom. And perhaps the more well-known representation or manifestation of fungi are mushrooms. Mushrooms growing in our backyards are cool, but definitely do not eat anything you find growing in your backyard because they could be poisonous. But mushrooms growing on us, on our bodies, or inside of our bodies, that's not so cool. So in fact, fungal infections are an issue worldwide. It affects about 1 billion people across the globe, with about 250,000 to 300,000 mold infections each year. Now, there are many different kinds of fungus, and I'm not going to go into the details of that, but what we're looking at here are mold-based funguses. So trying to detect this mold growing in the body, it's not an easy task. You could potentially do that in the lab, but even that process is not reliable. There are various different tests you could do, blood tests and different cultures, samples and all that you could do to attempt to detect mold growing on a person, but the reliability is not up to par to what we wish it to be. So we are looking at different modes of detecting fungal infections, and naturally we will fall on to CT scan data. And so this is where the fungal AI project comes into play. Our main goal here is detecting fungal infections, and specifically in the lungs. We are doing so not necessarily for diagnosis, but more for semi-automated surveillance. So hundreds of scans coming through a hospital, we want AI to be able to flag out these are the top 10 or 20 scans that we want a radiologist expert to eyeball before making a final decision. So we are not substituting the doctor, we are assisting in the surveillance strategy. So we are using CT scan for our purposes, and we are looking at using deep learning technologies to analyze the CT scans. So just some very high level introduction to the terminologies that I'll be throwing around over the next few slides. What you see on the right-hand side here, this is just a single slice of the lungs. So if you imagine you're looking at a person top down and you cut a person in half, this is what you will see through a CT scan. Now, a person is not a 2D slice, they are a 3D body. And so each scan of a person would consist of multiple, perhaps up to 100 plus, few hundred slices of what you see here. So in our first iteration, we did a quick proof of concept just to see, if AI is able to detect, even at the most basic level, these fungal lesions in the lungs. So we started off with just taking a convolutional neural network off the shelf. We use a DenseNet variant, which is just a variant of the well-known UNet architecture. And what we did was to perform segmentation. We get doctors to use a stylus on the screen to circle areas of fungal infections, fungal lesions. And then we get a neural network to predict through a segmentation process where those fungal infections present themselves in a slice. So we're doing this on a slice basis, not on a scan basis yet. So the problem with this is that, like I mentioned, the body is 3D, whereas what we're looking at is 2D. And so there's no 3D context provided in our first iteration. But that's another problem that we'll be looking at later on. So I will be showing images over the next few slides, but in general, the results were somewhat promising in that we were able to detect fungal lesions to a large extent, but at the cost of poor specificity, which means this loss of false positives. So I think images speaks 1,000 words. Here are some examples. On the left here are what the doctors have labeled. So in green, the green is what we're going to look at. The blue and the red is not so much relevant to us right now. So a doctor has come by, looked at this single slice and said, yeah, that is a fungal lesion. They took a stylus and they draw some markers around it. We fed that into the network and we get a network to predict pixel-wise where these regions are. And this is what, on the right-hand side, is what the machine has predicted. First of all, it's great to see that the predictions are all together. In other words, you don't have random pixels popping around the image. These segmentations are these are the raw outputs, so we have not done any filtering at all. So these segmentations are quite clean in the sense that they tend to aggregate towards each other. It has got a pretty reasonable circle of that fungal lesion, although there is a bit of a false positive on the right-hand side here. A few more examples just to give you a visual idea of how well the machine is performing. Here is something that the doctor has labeled, and this is what we get. And again, we're going to get the tiny little bits and pieces here that are false positives. So here's another example. Again, a pretty good circle of this and some false positives. Another example, in this case, the highlighted region is not too specific, but at least it's still got the fungal lesion. And again, more false positives. So I think you can start to see the trend here in the sense that what we got on this first iteration was not too bad. It picked out a lot of this fungal, but it is getting a lot of false positives. And keeping in mind that these examples that I'm showing you here are perhaps a little bit hand-selected and looks a bit nicer than what you normally get, but also that these specific examples here all show slices that actually have fungal in them, according to a doctor. But if these false positives present themselves so frequently, even in these slices, they do pretty much appear at the same rate in slices that do not have fungal. And slices that do not have fungal account for over 90% of the data set. So this is a major issue. If you consider all samples, all predictions that the machine makes, we get about a 1 in 3 false positive rate, which is quite high. So here are the challenges that we are looking at with this project right now. The first of all is that, and I'm going to go into detail each of these, but at a high level summary, the first of all is that this is a relatively rare disease. And although I say 250,000 to 300,000 cases a year, it's relatively rare because it is usually a symptom of another more severe disease. And it's therefore usually put to the sidelines while the main disease is being dealt with. And also because of this reason, many of these cases are not very well documented. So it's a rare disease, and that means small data sets, and small data sets generally mean that they don't go too well with deep learning. Secondly, we have a relatively low signal to noise ratio, and I will talk about that in a bit. So it is a problem of finding a needle in a haystack. Thirdly, it has very non-specific visual representations. So if I were to go back a couple of slides, and I were to just show this to you without any markings on it, and ask you to pick up which are fungal and which aren't, you can see that this problem could be a bit tricky. And last but not least, we have very low inter-rater agreeability, even between expert radiologists who have decades of experiences between them. So let me just go into a little bit more detail here. Small data sets. So as you recall, this project comes from the Alfred Hospital, and Michelle has been working on curating data sets of fungal infections for over the past decade. And in this example here, we are working with data from 2008 to 2017, which is about 10 years. And over that period, keeping in mind that Alfred is one of perhaps the largest hospital in Victoria by patient volume, and Victoria is a large state within Australia, we only get about 200 plus confirmed fungal infections in the entire hospital over the entire decade, which is really small compared to the larger number of patients that go through the hospital. We also can see that these data sets are quite biased towards older people and towards people with specific diseases. So there are multiple secondary factors that come into play when trying to detect that causes fungal infections in a person. So to deal with that, we are definitely looking at sourcing more data from multiple hospitals across Australia and also internationally, for example, from Box Hill Hospital and from a couple of hospitals in Singapore. The problem with that is, naturally, first of all, ethics and regulatory approvals are difficult to get us access to that data. And even if we have access to that data, more often than not, this data is not allowed to leave that hospital. And so we need to look at solutions on how to train models where these models are located across different locations, and perhaps federated learning is a solution to that, but that's a story for another day. Secondly, we have a very low signal to noise ratio. So just bringing up one of these slides that I've shown before, you can see that this fungal lesion, the one marked in green on the left here, is perhaps less than 1% of the entire image. So you could have use some smart techniques to just crop out the lung cavities, because fungal, what we're looking for only appears within those cavities on the left and on the right. But even then, these lesions could account for a very tiny portion of that lung cavity. And then keeping in mind that this is just a single slice. The number of slices in a scan of a person varies depending on the length of the person's torso, but could vary between, for our case, between 30 to 100 plus slices. And these fungal infections could appear in perhaps just one or two of those slices. So so here we are talking about a few percentage of a single slice, which is just a few percentage of the entire body. So it's a little bit like finding a needle in a haystack. And very importantly, these visual features are often non-specific. The cases that I've used here are a little bit more obvious to the non-expert viewer, but there are many cases which are non-specific and could be easily confused with other parts of the lung. For example, if I were to remove the markings on this slide and will ask you, is this region on the right lung fungal? You could make a reasonable guess that it is. And lastly is low inter-rater agreeability even between expert radiologists. So we did an informal study on how well the radiologists labeled the data, or how consistently they labeled the data between themselves. And this is what we found. We had 3 expert radiologists with decades of experience between them label 100 scans of these fungal infections. Then that included about 4,900 different slices. At the end, what we found is that at the scan level, and this scan represents an entire patient, it's an entire case, 40% of the scans had no consensus. So it's a bit worrying if you think about going to the hospital and you have a 40% chance that your doctors give you a different diagnosis. That is something worrying to think about. Now, I don't mean at all to underplay the expert opinions of the radiologists. Keep in mind that they are labeling these, which are a huge handicap. In practice, in the real world, they will make these decisions with the patient's history, looking at the patient physically. They would have results from other tests such as blood tests and various different scans and actual inspections of the patient. For our purpose of our labelings, we are restricted to making our decisions only on the CT image data. And therefore, that would explain much of the discrepancies that we have here. But nevertheless, it is still a problem that we are facing when trying to train a model. At the slice level, we get 563 slices that had no consensus among the 3 doctors. This might sound small in relation to the 4,900 slices in total, but keeping in mind that more than 90% of our slices have no fungal at all and are pretty easy to classify as no fungal. So this is a biased data set. If you consider only slices that was labeled as fungal by any one of the 3 radiologists, then you will see that 87% of those slices had no consensus. And the breakdown of numbers are shown down here below to give you a better idea. Now, to add to that mix is the way the doctors label these lesions. Pixel level annotations are affected by the manner in which doctors highlight the region. So for example, here we have a lesion that has been highlighted with some relatively gray area around it. So a bit of space around that actual lesion. And in this case, that is less obvious. And obviously, these changes between doctors, which compounds the challenges that we have. All right, so in the interest of time, I'm just going to wrap up at this slide here. This is a work in progress. That was iteration 1 that I've talked about. And what we are looking at right now is just quite a few different things. First of all, data augmentation and pre-processing strategies that we could use to augment and expand our limited data set. We are looking at pre-training, not just with data sets of fungal infections, but also various other CT scans out there. We could try to train a model with data relating to healthy patients and non-healthy patients in order to learn what is a healthy lung to start with. We could train, for example, with COVID data, which has symptoms that mimic fungal infections, and also with other diseases too. And as we move from a 2D training methodology to a 3D training methodology using the entire scan of a person, that requires larger compute. And so we are looking at training at scale using high-performance computing at Monash massive high-performance computing centers. All right, I'll leave it at that. And that's the end. That's all from me. I'm happy to take questions.
Thanks very much, Titus.
I have a quick question just regarding your last remark. You said going from 2D to 3D would require a lot of more compute. I'm wondering, is it worth going to 3D instead of just running multiple 2D networks? Because that's always a debated issue, because you would save a lot of memory and you probably don't lose a lot of sensitivity.
Yeah. This is feedback that we've gotten from the radiologists themselves, is that the way they look at this fungal, the way they diagnose where the fungal location is by scrolling through the entire 3D volume back and forth to get a feel for how things look relative to each other. And our hypothesis is that if we were to mimic the way doctors look at the data, that it would help. And so we don't have to provide the whole scan in. We could provide, an adjacent 2 or 3 slices, but we still think that it is worthwhile going into a pseudo 3D approach.
Thanks, Titus. We might have to move on because I think Sharif has now joined us. Hopefully we can sort of go back a little bit and fill in the gap. Just double checking, is that possible, Sharif?
Yep, I'm in.
Yep. Okay, great, thank you.
No worries.
Okay, so the next speaker is Sharif Tawfiq Abbas from Deakin University, talking about material discovery. We're pretty much on time. We're maybe 5 minutes behind, so we'll try and catch up a little bit if we can.
Okay.
Thanks,
okay,
everyone.
So I'll be sharing my screen now. Just give me a sec. Okay, so I'll be talking about work I've been doing recently on using machine learning to solve problems in material science. So the key problems I'm trying to solve is to predict complex material properties such as the band gap, for example, of materials, or thermodynamic or vibrational properties. And the way I'm going to be discussing this is, first I'm going to be talking about the data available. And whenever there is machine learning, whenever there is data, there is always a chance for having some machine learning happening, especially if this data has been produced in a consistent, in a standardized way. And the objective of what I'm doing now in machine learning is to basically, I'm not going to say, ditch DFT for, which is the density functional theory, the standard way where material scientists predict properties of materials, but maybe to support material discovery by using a highly efficient and quick method to predict material properties instead of having to wait online for computations using ab initio first principles calculations such as using DFT, which take a lot of time. So again, to put things in perspective, we have a lot of materials available, and people want to examine those materials for different properties. And to predict those properties, one would use methods such as density functional theory to predict the band gap, for example. But then calculating the band gap for a given structure using density functional theory or any other of those first principles approaches, doing this takes a lot of time. So instead of using DFT for a given material, how about we use a machine learning model that can mimic or can emulate DFT for predicting things that DFT is good at predicting, such as the band gap or formation energy or any of those quantities. So how do we do this? We have a lot of material published, available, free, online, downloadable material properties already computed using DFT, available online. Like millions of materials have been published online along with their DFT properties. So this means that both the inputs, which are the material structures, as well as the outputs, which are the material properties that we want to predict, both of them are available online. So this has opened a massive avenue for investigation by both computer scientists and material scientists to use all this data and crunch it, and produce interesting models for predicting with high accuracy, predicting quantities such as the band gap. Okay, so I'll just be very quickly going over those databases. So let's start with this one, Aflow, which currently hosts. That's an outdated number. It currently hosts more than 3,500,000 materials, along with their calculated properties. A lot of those materials have got band structures also calculated. So what people do is they produce or they invent a material, or they download a material from ICSD, and then they do with a standardized procedure, they perform the density functional theory calculations to produce the properties of the material, such as you can see here, thermal properties, elastic, Bader charges, like the partial charges on the atoms, band gap, band structure, density states, and all of these things. And then they save it on the database. So people, if you have a material that you have got from XRD, and you got some information about the composition as well as the the lattice structure, you can just maybe go on Aflow and look up. Maybe they have by chance. You could be lucky enough they have produced a material hypothetically, in the database that you already have, right? That's the same one that you have. And so this exercise of coming up with hypothetical materials and then finding if they actually exist in nature has been going on for a while. And now that we have this massive number of materials, so we've got here in Aflow, and also we've got in the other project, materials project, which is basically the one I use the most. Materials project has more than 130,000 materials along with their DFT calculations. So, and also there are other databases. So these databases, they provide, as I said, a large amount of pre-computed DFT data. So what we need to do is to solve the featureization problem, to find a way to represent this data, the structured data, to a machine learning algorithm. Okay, and the machine learning workflow would be, first you come up with this algorithm, featureize or represent the data into, as a string of numbers to a machine learning model, train the model against a certain quantity that you want to predict, and then test your predictions, and then you can get a model that can predict a quantity such as the band gap. However, what I've been finding in these databases, that there are, because of the standardization of the procedure, there are a couple of gaps in the data and also the procedure. The one gap is that they use a procedure, density functional theory procedure, that doesn't realize or doesn't understand van der Waals forces. So materials such as 2D materials like graphite, for example, you would get, the DFT computed properties of graphite or boron nitride, which are layered materials. And they're materials, a critical aspect of those materials is the strength of the gap, of the force holding these materials, holding the planes or the sheets of these materials together. So if you use a method that doesn't really account for this strength or this bonding, it's a very weak bonding, but it becomes significant for 2D materials. If there is no way to account for it, you get problematic, or you get inaccurate representation of the distance between the layers of that material. And that's why materials that are deposited on these databases that are mainly held together using van der Waals, for example, they usually have inaccurate structural and energetic properties. So they had to do with, either they apply van der Waals or they don't, right? So they decided they don't apply van der Waals, and there are good reasons for not applying van der Waals in the standardized procedure. One big reason is that it's hard to find consensus on one specific van der Waals, flavor of van der Waals calculation in DFT. You would find people arguing that D3 is the best, but then there is SCAN plus RVV10, which has been produced recently, and it's really, really good. And still, the field is still, flourishing with new van der Waals implementations or implementations of the van der Waals, interaction in materials, and it was a bit hard to, to maybe settle on one of those. So they just, did without any van der Waals. The other thing in these databases that's lacking is thermal properties. You would find some thermal properties for some materials in these databases, but some of the thermal properties require very, very expensive calculations, particularly, for example, entropy, for example, or the stability, vibrational stability, because these require that you calculate the phono modes or the vibrational modes for a material, which take a lot of time and a lot of resources. So at this moment, there are only almost 1,500 materials out of the 130,000. A lot, that have been, that have their phono modes calculated in materials project. Only 1,500. That's because it takes so much time and energy and resources to do that. Okay, but the thing is, if you don't have the vibrational properties of materials, you don't really know if a material can be synthesizable. A material that's synthesizable is a material that should be able to exist, and a material that can exist it should be stable, vibrationally stable, which means that at least it doesn't have any, imaginary phonons in its vibrational spectrum. And this information we only know for 1,500 materials on the database, but we don't know for almost 3.5 million materials. So machine learning can help fix these things, and that's stuff I've been working on, in my machine learning projects. So just to quickly discuss the machine learning workflow. So in machine learning, you learn properties from available materials, right? So you have a material, you turn it into descriptors, and then you use those descriptors, feed them into a model. So we have descriptors and models in machine learning, right? Now, descriptors in chemistry in general, there's a long history of generating descriptors, QASR and all this field of research, where descriptors of chemical compounds, also called chem descriptors, or there are a couple of names for those. If you have a chemical compound like carbon dioxide or whatever, it's just zero-dimensional, so it doesn't repeat in space. It's just one isolated molecule. There are so many different ways to represent it to a machine learning algorithm. And when I say represent it to a machine learning algorithm, I'm mainly speaking about expressing it as a string of numbers. So instead of just carbon dioxide, just a string of numbers. And there are many different ways to do this, but for crystals, this has been a very, very difficult challenge. I'm going to have to skip this bit. Understand that there's a time limit, but we can discuss it offline. Why are crystals more difficult to represent to a machine learning algorithm than molecules? Remembering that crystals are pretty much like molecules, but they are three-dimensionally periodic. So they repeat in all dimensions, whereas a molecule doesn't, right? And it is this periodicity issue that made generating descriptors for crystals a bit difficult until in 2017, Alexander Isaev, who is a collaborator of mine, they published this amazing, very well cited paper as well about a new set of descriptors that represents crystals, and it achieves very, very high accuracy in predicting the band gap and a range of other DFT computed properties. So I collaborated with Alexander in order to predict properties of 2D materials. Remember when I said those databases lack the the representation of the van der Waals interaction in 2D materials. So I was working on a project where I'm basically building Lego-like 2D materials. You see this image in this beautiful perspective by Geim, where you get a HBN or a hexagonal boron nitride sheet, and then on a graphene, and then on an MOS2, and then you build a totally new exotic material. Then I worked on a project where I was building bilayers of materials, or let's say hybrid 2D materials. And I wanted to predict for any given hybrid 2D material like MOS2 and WS2, what is the interlayer distance? So it's a geometric property. And what is the band gap, an energy property? And for a project like this, there could, given that there are almost 6,000 2D materials available, both hypothetical and realized, available in online databases, we could have almost 20 million possible hybrid, van der Waals materials or bilayers. So we cannot really use DFT, for example, to predict the properties of all of those bilayers. So one thing to do is to use machine learning and to train a machine learning model on a small number of bilayers. And in this project, I had only 267. I'm calling it Lego 2D materials because I basically got any two possible materials that can be commensurately placed on each other. And there is, of course, a detail and a technical detail related to which ones to pick for this, for this data set, 267 materials. Has to do with the size of the supercell and all that. We can discuss this offline as well. So it's a very small data set, but machine learning was able to predict those two quantities, the energy band gap and the interlayer distance, with a very high accuracy. And this work went into advanced 3D simulation. It was also collaboration with Alexander.
Just one more minute, just 1 minute if possible.
Oh yes, so thanks. The other project was predicting, just quickly, vibrational properties. So for those, remember I said 1,500 materials along with the vibrational properties are available. So again, collaborated with Alexander to predict the vibrational properties of those materials, and again with very high accuracy. Now, at this stage, what I'm working on is just to be able to use machine learning to predict the synthesizability, or strictly speaking, to predict whether a material is stable or not stable. And that work is currently in progress. The very difficult bit in this work is to find the right features to represent the materials to be able to predict whether a material is stable or not stable. But at the moment, I'm getting almost 0.86 in the range of 0.86 area under the curve in the classification using my present features. And currently doing more work, developed crystal features, set of descriptors available on GitHub, and currently developing further features to identify lithium conductors, lithium conducting materials. Yeah, and that's all from me. Thanks everyone for your attention.
Thanks very much, Sharif.
Always.
I think in the interest of time, we'll just keep moving. And if anyone has questions for Sharif, we can come back to them at the end of this series. There hopefully will be a little gap at the end for discussion. It's worked out nicely because we've now got a theme going in this section of the presentation. So the next speaker is Tu Le from the School of Engineering at RMIT on a similar topic on discovery of materials and predicting properties. Thanks, Tu Le.
Thank you, Adam. I will share my screen. Can you see my screen now? Yeah, cool.
Yes.
Hope it's better now. So good afternoon, everyone, and thank you very much for the invitation to present to you today. As mentioned, I work for the School of Engineering at RMIT. Prior to working at RMIT, I was a research scientist at CSIRO. Over the last 10 years, I have worked extensively in the area of materials development using machine learning approaches. I'm very excited to share with you today some of my studies, which of course focus on employing machine learning to explore the vast material space. So up to now, I have mainly used artificial neural networks for constructing machine learning models. What I found is the use of informative and relevant input parameters for the materials is much more important than the choice of machine learning algorithms. If I have good input parameters, I get good models. If I have bad input descriptors, regardless of the algorithm, I still get bad models. Imagine we want to build a model to predict the price of the cars. The output of the model is, of course, the price. The input would be parameters that describe the cars, such as the number of seats, the number of doors, the type of transmission, the body type, or the brand. If we want to build a model for a human, then we can use inputs describing the humans, such as the height, the weight, the body shape, the arm length, etc. If we want to build a model for molecules, we can use inputs describing the molecules, such as the molecular weight, the shape, the volume, the number of different types of atoms inside the molecules, or the number of different functional groups, or total polar surface area. For materials, to build models predicting properties of materials, as inputs, we can use parameters describing the structure of the materials or the experimental conditions that are used to make them. And the ultimate goal is to accelerate the design and development of new materials by predicting properties of new materials prior to synthesis, or gaining more understanding on the relationship between the material structure or experimental conditions and the material properties. So the first case study that I would like to share with you today is about using machine learning to design a novel material with high flash point. When I was involved with a project with Boeing about 5 or 6 years ago. So Boeing wanted us to design a material that satisfied 5 strict criteria. And one of those was the flash point has to be over 155 degrees C. My part in the project is to give an estimate of the flash point for potential compounds or potential materials that already satisfied the other 4 criteria. So I compiled a data set of over 9,000 compounds, Most of these come from the TST data of the Environmental Protection Agency in the US, and the rest came from different journal papers. And these compounds have the flash point vary from less than minus 130 to over 900 degrees C. They are also very diverse in terms of chemical structure, molecular size, and physicochemical properties, as you can see in the histograms on the right side of the slide. So together, I used close to 800 structural parameters as input descriptors for the models. 80% of the data was used to train the models, and 20% was used to validate the models. The table at the top of the slide shows the statistical results of the best linear and non-linear models. The R-square values for the training and the test sets are quite high. The errors of estimation or prediction are quite low. In fact, these errors fall in the range of the experimental error. So no models can do better than the actual measurement. So these fall in the ballpark of the experimental measurement error. The figures at the bottom shows the measured versus predicted flash points for the training set and for the test set. The closer to the diagonal line these data points are, the better the predictions are. So these models do pretty well. All data points are closely aligned along the lines. So I used these models to estimate the flash point of potential compounds, and my colleagues then synthesized the lead candidates for further testing. We successfully designed the material, and the industry partner funded us to do the scale-up stage. Oops. While mining this data, I also identified a small subset of data where the flash point was wrongly reported in the TEST database. This column on the left here shows the flash point predicted by the neural network models. The column in the middle shows the flash point reported in the TEST data. And the column on the right presents the flash point reported by other sources of publications. And these flash point values are very close to my prediction. So the models are not only good for making prediction, but they're also good for identifying errors in the data. Here is another example where I used machine learning to predict the toxicity of zinc oxide nanoparticles. You might have already known the zinc oxide nanoparticles is a common ingredient in cosmetics and sunscreens. However, some studies have shown that these nanoparticles can be toxic. To reduce the toxicity, many types of modifications to the pristine nanoparticles have been developed, such as using surface coatings or dopants or altering the aspect ratios of the particles. It is extremely difficult, if not impossible, to test the toxicity of the vast number of possible modifications. Therefore, the development of rapid computational models for predicting the toxic behavior of nanoparticles is important and timely. In this study, we looked at a library of 45 zinc oxide nanoparticles with different characteristics. They were calcinated at different temperature, doped with different metals, or coated with different materials such as serum protein or silica or oleic acid. They had different volumes, surface areas, aspect ratios, and so on. And all these differences were reflected in the inputs of the model, as you can see in the table on the left here. The output of the model was the cell viability or other bioresponses describing the toxicity. As you can see from the lower graph on the right, the predicted and measured cell viability values are almost identical. The upper graph shows the prediction results for 8 different nanoparticles. With this kind of models, we could reproduce the cell viability curve. From that, we can calculate the IC50, which is the concentration at which 50% of the cells die. IC50 is commonly used as an important indicator of compound toxicity. We also looked at the cell membrane damage described by a parameter called the LDH level. And these graphs illustrate the measured versus predicted LDH level using multiple linear regression and neural networks. Clearly, the neural network model performs significantly better with all data points aligned closely along the diagonal line. However, the performance of the linear model is reasonable. So we could use the coefficients of the linear model to quantitatively rank the contribution of different factors on the cell membrane damage. And this kind of information is useful for the design of safer nanoparticles. I have also used machine learning models to study antifouling materials. As you might already know, protein absorption is a common but complicated phenomenon. It is a multi-billion-dollar problem in industry, and we have not yet found a solution. And we get fungi and other living organisms on our roofs, on our solar panels, on our pipes, on our ships and boats. About 15 years ago, George Whitesides and his colleagues at Harvard came up with a set of rules for designing antifouling materials. These are usually referred to as the Whitesides rules, and they are very commonly used. These rules suggest that bioinert materials should have polar functional groups, hydrogen bond acceptor groups, but no hydrogen bond donor groups, and no charge. The Whitesides rules were derived from a study on self-assembled monolayer with various terminal groups. So these include hydrophobic and hydrophilic groups of different types, such as ethers, amines, amides, sugars, and nitriles, so different type of chemical structures. Out of curiosity, I built some models to validate the famous Whitesides rules. These models use molecular inputs as stated by the Whitesides rules, but using these, I did not get very good results. The R-square of the model was only about 0.4. I replaced the hydrophilic factor suggested by Whitesides with log P, which is also an indicator of the molecule's hydrophilicity or hydrophobicity, and I still got very bad statistical results. But when I use the standard approach that I would use for any other data set, which I calculate a pool of molecular descriptors describing the difference in the chemical structures, and then I use feature selection algorithm to prune out irrelevant descriptors and build machine learning models with the relevant descriptors, I got much better results. The R-square values reach about 0.8, and the errors of prediction are down to as low as 13%. Whoops, I went too fast. The model also provided ranking scores for different factors, and I would pretty much wanted to call this the two less rules, which are of course an extension to the Whitesides rules. I have also used machine learning for ionic liquids, and there are an estimated about 10 to the power of 18 configurations of possible ionic liquids, leading to difficult and time-consuming experimental work for identifying potential ionic liquids for targeted applications. And these numbers become even larger. The compositional space becomes even larger when we add the effect of additives, molecular solvents, or solutes into the ionic liquids. So to thoroughly understand the structural property relationships of ionic liquids and develop new models for predicting properties, we need novel data analysis techniques to investigate the reported experimental data and explore the vast ionic liquid space. And in this space, I have used machine learning models to predict different properties of ionic liquids, such as the surface tension, viscosity, and conductivity, using data from high throughput robotic experiments, as well as data compiled from the published literature. And I have used the obtained models to predict properties for larger libraries of ionic liquids that were not yet synthesized. And my colleagues subsequently synthesized and characterized a small selection of these new ionic liquids to validate the prediction results. And the results were very promising. So the tables here show the statistical results for 4 properties: the surface tension, the pH, D1 and D2, which are the distances between the head groups of different materials when they self-assemble in ionic liquids. So the R-squared values for these data sets were quite high for both acid-rich and base-rich samples. These plots show the measured versus predicted data, and as you can see, we have quite good accuracy. And we use the obtained models to make prediction for 960 new solvent combinations. So same ionic liquids, different acid to base ratios, and different water concentrations. The neural network models perform very well for these new data. As you can see from the table here, This column here shows the measured surface tension. And this one is a prediction from the neural network model. And the last column here shows the difference between the two. So you can see the difference is very small for the majority of the cases. I have also used machine learning to make the prediction for the rate constant of an organic reaction that happens in 36 different ionic liquids. But I think I'll skip this in the interest of time. So last but not least, I want to share with you some results I've got for organic photovoltaic materials. A paper which came out in early 2018. It studied 280 small conjugated molecules using machine learning, and the authors proposed 13 descriptors, mostly calculated using DFT, and predicted the PCE, the power conversion efficiency. As you heard from Sherif's talk, DFT is usually very resource expensive and time consuming. So with this paper, we wanted to show that we can achieve similar accuracy in terms of machine learning models prediction using some simpler descriptors, some simpler input parameters that can be calculated much faster than DFT parameters. So we had a very talented undergrad student who did this project in 2019. His name is Joel Park. He constructed the machine learning models for the power conversion efficiency, the open circuit voltage, the short circuit current density, and the fill factor. All these are very important properties in terms of judging the properties of the photovoltaic devices. We use
just 1 minute too.
Yeah.
1 minute left. Thank you.
Thank you. Using this exact same machine learning algorithms, our models can achieve very similar performance compared to the models that use quantum descriptors. And we are looking at expanding this project further by compiling larger data sets and probably developing new input descriptors to improve the performance of the models. I'll skip those. With that, I would like to thank my colleagues and collaborators. Without them, the work would not have been possible. I also want to thank the collaborators at home, although they are not always cooperative. And thank you very much for your attention.
Thanks, Tu. That's great. Great work. We do have a question from Nima. How generalizable are traditional machine learning methods over the noise in the data that you highlighted? Did you conduct any parameter studies to identify the tipping point in terms of the data set size for the model to be able to generalize and identify the noise in the data?
So usually with the materials data, the data sets are very well, characterized in the lab, and usually they come from the same lab. Or if not, the condition of the experiments are reported in the published paper or published databases. So we usually don't get a lot of noise. And if there's noise, the number of outliers usually really small. In terms of using the model to, make new prediction, we can only, apply the models for materials that have probably similar chemical structures. So it has to be within the domain of the model.
Thanks, Tu.
No worries.
We will need to move on. So our final presentation for the day is Gavin Rice, who was previously at UQ at the Institute for Molecular Bioscience, but is now at the Max Planck in Germany, very famous institute. If I can, Gavin, can I ask you to aim to finish at let's say 3:52? That'll give us some time. That's, well, you just got an extra minute by my clock. Let's say 12:53.
No worries.
That'll give us a few minutes to discuss at the end.
Yep, no worries. I'm just going to have to actually quickly leave and rejoin so that Zoom has permission to access my screen. So I'll be right back.
Does anybody want to throw in a quick question while we wait for Gavin to return? For any of the previous speakers? molecules. You are muted, Gavin.
Thank you.
That's it.
Okay, and you can see the screen. Very good. Thanks, Adam. As you mentioned, my name is Gavin Rice. I'm going to be talking to you about some research that I did while doing my PhD at UK's Institute for Molecular Biology. And I'd like to thank the organizers as well for giving me the opportunity to come and present to you today. And I'd like to start by giving sort of a brief introduction to the technique we use, as well as the problem that we were hoping to solve. And this is a technique called cryo-electron microscopy. And I got started in this technique during the first year of my PhD in 2017, about a month after these three gentlemen here on the left won the Nobel Prize in Chemistry for their contributions to the development of the technique. So it's a very exciting time to be getting involved. And fundamentally, cryo-electron microscopy is a tool for capturing images of biological molecules at atomic resolution. This is something we can apply to individual protein molecules up to small cells. And the idea is to use image processing to convert these 2D images that we capture into 3D reconstructions of these interesting biomolecules. Just going quickly through the pipeline, your starting sample would be either a purified protein or a sample of a single molecule, or even now small cells, and the larger limit is getting bigger at the moment. But the idea is that you put one of these samples into the cryo-electron microscope, and what you get out is one of these 4K by 4K images. And in these images, all of these little black dots here are actually 2D projections of, in this case, GRO-EL, or a biological molecule. And in these images, 1 pixel corresponds to about 1 angstrom. And for some reference and to give you some scale, 1 angstrom is 1/10 millionth of a millimeter. So these are quite small. And the idea is that by sampling many different angles of the molecule, you're able to then use weighted backpropagation to reconstruct the 2D images into a 3D volume at high resolution of your biological molecule. You're able to do this for something like a ribosome, which is the protein in your cells responsible for reading RNA and putting together amino acids to build proteins, up to things like a microtubule, which is a part of the trafficking network for proteins within your cells. And the idea is that by solving these high resolution 3D structures, we can get some sort of idea about their conformational dynamics and their actual molecular functions, and their normal functions, as well as what goes wrong with them when you have certain disease states. And this obviously has impacts for human and animal health. So what's the problem here? And first, I'll show you the image on the left, which is one of these 4K by 4K images that you get out of the electron microscope. And this image contains many individual molecules of our protein. And you'll notice that the signal to noise is very low in these images. And a typical data set would probably consist of about 6,000 to 10,000 of these individual images. And the first thing you need to do in your data processing pipeline is you need to segment these images. You need to identify each of the individual molecules so that you can crop them out and then average them together to get the 3D reconstruction. And of course, with 6,000 to 10,000 of these images and maybe 200 to 500 molecules per image, you're not going to be doing this manually. So we have some automated segmentation methods like template matching, Laplacian and Gaussian, and even some deep learning methods like YOLO. But all of them share a common theme that is generating a very large number of false positives. So they'll pick all your molecules, but they'll also pick a lot of background noise. If there's any contamination in the image, if there's some of your molecules have degraded, they'll also pick that as well. And this is a problem because the next step of the pipeline, we use something called k-means clustering to clean up our data set. And what this is essentially you select a certain number of classes and your data is subdivided into this many classes based on how similar the molecule images are to each other. And what happens is when you have a very large number of false positives, this doesn't work very well. So looking over here on the right, this is 2D classification of a molecule called TRPV5. And this is an ion channel that is found in the human body. Is actually it's responsible for sensing capsaicin. So if you've ever eaten something very spicy, that sensation of spice that you feel is due to the activation of this molecule. And in these two classes, we see quite nice images where we have really good molecule images are being averaged together. So this is a view of the molecule from the top. It sort of looks like a donut from the top. And from the side, we can see that it looks like a donut with some things sticking out. But the rest of these averages are clearly corrupted, and they're corrupted by the false positives in the data set that are being averaged in with the good images. And this means that you can no longer use these to go to high resolution in 3D. The other issue with this is that when you have millions of high resolution single molecule images, there's a really significant computational cost that comes with this. So this is clustering averages I ran on about 500,000 particles. This required 2 terabytes of RAM, and on running on 4 GPUs on UQ's HPC Wiener, this took 24 hours of wall time to compute. So what is our solution to this? So while others were focusing on the segmentation problem, developing things like YOLO, I thought it would be interesting if we instead focused on a method to clean up the results of the segmentation. So the goal was to build a classifier to efficiently filter out false positives that were created during segmentation. To do this, of course, we need some training data. So I manually labeled a set of 1,000 true positive and 1,000 false positive molecule images that I had generated using a template match segmentation method. And this was split into a 70-30 training validation split. And here you can see examples of the true positive images and the false positive images. And I promise you, if you cannot see it, eventually, if you stare at these long enough, you'll start to see little donut shapes that correspond to our molecules. And then I also manually labeled another set of 1,000 images that we use as an evaluation set. And with this, the goal is to build a 2D convolutional neural network classifier that can take in all of these images and separate them into true positives and false positives. And we were able to do this with quite a high accuracy, as you can see from our receiver operator characteristics. And the network architecture we used to do this was a very simple 2D convolution neural network where our images are passed in. We have some convolution layers that have 2D convolutions and rectified linear activation functions. We use some average pooling. At the end, we flatten out, and then we have a final dense layer, which has one output layer and a sigmoid activation function to give us a single value for each particle. And this single value between 0 and 1 actually correlates to the quality of the image. And this is exactly what we were hoping for. So what you can see here is that on the left, I have done this k-means clustering, but only on particle or molecule images that were given a score by the network greater than 0.9. And you can see that we have very nice k-means clusters. And you could use these to now go on to the 3D reconstruction. And what we also saw is that if you look at the very worst scoring molecules, we see that these are indeed our false positives. And so we've correctly created a classifier that is able to separate and distinguish between our good molecules and our false positives. And what's better about this is that the prediction time now for about 500,000 images is down to 4 hours running on a single graphics card. So I'll talk about the outcomes of this project, and then I'll speak a bit about some of the challenges that we faced and some of the future directions as well. So first outcome is that obviously we were able to build a classifier that effectively and efficiently classifies true positive and false positive molecule images in cryo-EM datasets. The code for this is open source and available on GitHub. There's a manuscript we've created for peer review, which is ready for submission. I'm hoping to submit very soon. And this tool has actually already been picked up by a popular greater EM image processing suite called Spire, where they're hoping to integrate it into their package. This project actually ran at Health Hack Australia 2020, and we were able to take second place. And I'll talk a little bit about more of that in the challenges section on the next slide. And then the last sort of outcome and future direction, which is more personal to me, is that this experience helped me secure a postdoc position at the Max Planck Institute, where I have what I consider to be my dream job, where I'm working 50% on structural biology and 50% on continuing development of new machine learning tools. Talking about a few of the challenges. So I think one of the major challenges for this project and in general, when you're in machine learning adjacent research disciplines, is how do you get really good training data? For example, our single molecule images are pretty distinct and they have very low signal to noise. And I think that if you, we actually tried using a 2D convolutional neural network trained on something like FaceNet or ImageNet. And then they don't perform very well. And so you need to curate some very good training data. And actually, in the end, I actually tailored this project around this challenge. At the time, I had a few different ideas of different areas of the data processing pipeline for our workflows of where we could apply machine learning. And I chose this one because I knew this would be the easiest place for me to actually create these labeled training sets. And then the next challenge we faced was how to find ML talent and how to pitch your idea. So I'm a neuroscientist and a structural biologist by trade. I'm not a computer scientist. But through some courses like the Monash Introduction to TensorFlow and Deep Learning, as well as some more involved courses through things like Coursera, I was able to learn quite a bit about machine learning and neural networks, but not enough to actually do any of this myself. So I pitched the idea at last year's Health Hack, which is a hackathon competition that normally runs for 1 week, but last year ran for 2 weeks because it was being held virtually. And the idea is to bring together and pitch ideas for health-related tech problems. And the hope is to, in that time, bring in experts in the field and develop a product in that very short period of time that can have some impact on human health. But this project was sort of an outlier there. I mean, I'm able to tie it in because cryo-EM, the 3D reconstructions can have implications for human health. But a lot of the projects that go to this sort of hackathon are things like health apps that really have direct translations. And this was really a thinly veiled research project, but nonetheless, we were successful in this. Another challenge we're currently facing actually, so funding and support for these smaller ML projects. And I mentioned we have a manuscript, and one of the questions we're asking now is how are we going to pay an open access fee? Obviously, we'd like to bring this to an open access journal. But that's sort of an issue if we need to pay $3,000 US in open access fees. And then the other challenge, which we were very lucky not to face, is that you might have to pay for compute time. Thankfully, since processing our data already requires HPC, we were already set up on UQ's HPC VNer, and we're able to utilize that resource. And then just 2 very quick observations that, and then I'll take questions. And I think that the first one is that explainability is particularly important when answering research questions. I think every talk I've given about this topic, particularly to biologists, they always have the questions of how exactly is your neural network able to differentiate between the true positive and the false positive. And I think for something like a classifier, this is relatively simple. We can say that we've taken each pixel and projected it into a matrix, or taken each image and projected it into a matrix where each value corresponds to the contrast of a pixel in grayscale. And the network is able to then learn the higher order symmetry that makes all of our TRPV5 molecules different than the false positives that are being picked. But I think in a lot of cases, this explainability is not quite as easily found and is something that we need to pay very close attention to. And then the last observation is just that even basic ML techniques can have a really strong impact in ML adjacent research fields like structural biology. So we used a very basic net-like 2D convolutional neural network architecture. We weren't using a super advanced transformer model or a generative adversarial network. We were still able to have a fairly impactful result just because of the place where we applied this technique to really fill one of the bottlenecks in our data processing workflow. And with that, I'd like to just acknowledge a few people, particularly the CryoFilter dev team. So Simon, Mahasan, and Prithvi, who were involved in the project during Health Hack. And then highlighting Simon here, who's is a PhD student in Nick Hamilton's lab, who's a fantastic software developer who really did much of the coding involved in this project, as well as my support at UQ, so my supervisors, as well as Nick and Jake and Irek at the HPC Center, as well as Health Hack Australia for giving me the opportunity to pitch this idea and get this product developed. And finally, Monash's Introduction to TensorFlow and Deep Learning workshop, which was sort of my very initial introduction to deep learning. And with that, I'd thank you for your attention and take some questions.
Thanks very much, Gavin. And yeah, it's great to see the value of things like Health Hack and also the training that's being offered nationally through this ARDC project. We had hoped to have a little bit more time than we do now to have a general discussion. We do, Tarun wants to speak for a few minutes just to let you all know where we go from here and which activities are coming up next. I think we might have to go straight to that, and if we end up with time at the end, we can open up the discussion.
Yep, thank you, Adam. I'll try to do it quickly. Firstly, about the POSE internships. So POSA is doing their call for internship projects for their summer vacation students. So if you know anyone with an interesting project, please pass this link on to them. And next thing is the ML practitioners and trainer pool. So on the ML for EU ML Corp website, there are ML practitioners and trainer pool web pages. So go have a look at those pool pages, and if you would like to be a part of the pool, then put down your interest. And if you are interested in running a workshop, and if you're looking for trainers, then you do know where to find the trainers. So that's something which we wanted to put it across. And we have another talk at C3DIS next month, I think. And ML Corp has submitted an oral presentation. Dr. Nick from UQ, Komati and Kaiwa from Monash will present at the event about the ML Corp activities. And these are the upcoming trainings we have as part of the ML Corp, ML for EU. I mean, if these trainings are open for all, so if you are interested, do register. And all of these details are mentioned on the website. And the next planned showcase event will be on the 5th of August. So there are no more registration details or anything as of now. Make sure you subscribe to the mailing list. And if there's anything set up, you should be getting an email, and you can register for the event. And lastly, I will be sending the recording of the event. If you have missed something and if you would like to look back, you will have a recording. And with that, I'll also send a survey link. It'll be great to get your feedback on this format, the topics involved, the quality of the talks, what did you like, and how can we improve. So if you have any thoughts, please do fill in the feedback form. It'll help us design the next showcase event in the way it will be useful to the community. Yeah, with that, I think we can move ahead to any questions if anyone has with respect to the updates or the projects.
Seems we're just coming to a close, but the overall objective here was to really get a lot of people together that share a common interest. So in this case, the focus was on imaging, more generally machine learning. If you have questions that you didn't get time to ask today, please contact each other directly and have that conversation. Or as you've heard from Tarun, there are lots of other activities that are on the horizon. So it's just one of many opportunities for us to be discussing these things. And hopefully we can do more things in person in the coming months if things go well. Let's see how that goes. So unless anyone wants to add anything else from the organization team, we might wrap up. Let me know if anyone has anything else they need to put forward.
No, probably I'll just add a few sentences there. Thanks everyone for participating. I think one event we're looking for is how do we wind up the series of showcase events happening in the next couple of months towards the eResearch Australasia. So there's planning in progress to put together probably a half-day event for this community to come together, look at challenges, look at success stories, look at some panel discussion. So any ideas you have, please do share with us. Thank you. And thanks to the chairs today.
Thanks, everyone, especially to the speakers. Thank you.
Thank you.
Bye.